What's going on, everybody? This is Mr. Diamond, and we're going to get ready and go through our Section 2 of Chapter 0 notes. We're not going to go through all of it. We're going to just get up to what I think is a good stopping point because I want to talk about one of them in a lot of detail. This is one of my favorite things to talk about in all of chemistry. So this is Section 2, titled Making Stuff Up, and that's might give you a hint as to what we're going to talk about. So if you think you know, I guess you could make a guess and then email it to me or put it in a comment, but that seems like a waste of your time. We are, in fact, talking about these things right here. I guess I shouldn't motion forward. I guess these things right here. And looking at them, you probably recognize, let me switch to my cool pointer again. You probably recognize this thing, and then these all look a little bit weird, and you may not really know what's going on here. But based on these two, I'm sure that a lot of you are guessing, oh, well, these are all atoms. And you would be correct. They were all atoms. But we're going to start at the very beginning. You may think, okay, well, atoms have probably been around for maybe 100 years. We've known about atoms. Maybe a little bit more than that. I really don't know where your opinions are of how old or new atoms are. But the term for atom, and the first person to ever propose the idea of atoms was Democritus in about 400 BC. So that's like 2,400 years ago instead. And he coined it from the Greek term atomos. Atomos means individual or indivisible. And we give Democritus credit for giving the idea of the atom, even though he didn't discover anything. It's not like he was sitting there with his Greek microscopes made out of stone and trying to look at little bitty atoms. Basically, he was a philosopher, and he proposed, or he had the thought that in theory I could take a piece of cheese or a piece of bread or a piece of rock or whatever, and I can keep cutting it or breaking it and smashing it. I can get it smaller and smaller and smaller and smaller and smaller and smaller, and eventually there has to be a point that I can't do that anymore. It logically would not make sense that I could infinitely be cutting it down into smaller pieces. So he said that there must be a piece of something that cannot be divided. It is indivisible. It is atomos. A meaning not, and then tomos be divided or divisible. So as you can probably guess, that means he didn't actually have any idea about atoms. He just proposed that that type of thing must exist. And thousands of years later, when people finally started researching it, they were like, oh, dude, this guy was super close. That's kind of crazy. We're going to give him some credit by calling them the atom for the Greek atomos. So by the 1700s, we actually knew that elements existed, which might be a little bit earlier than a lot of you probably thought. But they knew that these were the smallest things that you could break something down to, and they were the fundamental pieces of chemical reactions. For example, they knew that you could smelt down and you could get a piece of solid copper, and once you had it as copper, that was as pure as it was ever going to get. It was not going to become more pure copper. It wasn't going to turn into something else, or it wasn't going to turn into two pieces. And they also knew that not everything was necessarily an element. They knew, for example, about alloys and things like that, and that's why they knew that certain things could not be broken down. And they thought this was the smallest you could go. This was that just getting to an element was as base as you can get. They also knew things such as the fact that, right here, you can take two elements and combine them together to get something new. Now, don't quote me on that they knew that hydrogen and oxygen could be combined to make water. I don't actually know when that piece of knowledge entered the human consciousness. But this is just a very basic formula of you can take two elements and you could put them together and get a chemical reaction out of it. So these three laws at this point were more or less how we understood chemicals to work, or elements to work. We have the law of conservation of matter and energy, which I'm assuming you've heard, law of definite proportions, and law of multiple proportions. I don't know if I actually go over them. Let me click up here. Yeah, I don't. Okay. So I'm going to give you a brief definition of what each of these three are. They're not a huge deal. I'm not really going to make you know all of these for a test or anything like that. Law of conservation of matter and energy, I assume you feel comfortable with. Matter cannot be created or destroyed. Energy cannot be created or destroyed. They only change forms. Law of definite proportions states that there is a definite proportion in every chemical compound that is created. So, for example, when water is created, it is a definite proportion of 2 hydrogens to 1 oxygen. That is the ratio to make something water. It needs to be 2 to 1. You can still have hydrogen and oxygen combined together, and it may make a new compound, but it will not have 2 hydrogens to 1 oxygen. Because if it did, it would be water. And the reason for that is the law of multiple proportions. If 2 things are made out of the same exact elements, they must be in multiple different types of proportions. Water is H2O, hydrogen peroxide is H2O2, hydroxide is OH with a negative charge. All of them are made of O's and H's, but each compound has its own specific proportion, and being made out of the same thing, being a different compound, means that there are multiple unique of those proportions that are used. Again, you don't really know this a ton. This is just kind of the baseline of where they were at. And then Dalton came along, and Dalton was pretty much the first actual scientist we give credit for doing a real breakthrough on the atom. He wasn't just standing around thinking, oh, this probably exists. He actually was doing research, and he actually came up with a 5-part law that we're going to be analyzing here. So the first part of the law, all matter is made up of tiny indestructible particles called atoms. Number 2, atoms of a given element are all alike. Atoms of a different element are all different. Atoms cannot be divided, created, or destroyed. Atoms combine in simple whole number ratios to form compounds. And in a chemical reaction, atoms or compounds are combined, separated, or rearranged. So my question to you is that probably sounds pretty good, but there are some problems with it, and I want to see if you can figure out what the problems are. So I'm going to back up to this page again. And I'm going to leave it up there for a little bit. If you want to pause the video and try to think about it before I give you the answer, you're welcome to do so. But let's think through. I'll tell you there is at least one problem with this theory of how the atoms work. So I think that's enough time. You probably pause the video if you actually wanted to think about it. So let's go point by point. So all matter is made up of tiny indestructible particles called atoms. All matter is made up of atoms. We know that. But tiny, well, yeah, I guess they're small. Tiny doesn't even seem like it gets to the point of it. I feel like they're even smaller than tiny. But indestructible particles, well, we know that's not the case because we do the atom bombs, splitting the atom. It's a thing that we've done. So indestructible is a problem. They are not indestructible particles. They are, in fact, destructible. And because of that, we can go down here, and atoms can be divided. They can't be created. They can't be destroyed, but we can divide them. So that is one change that we can do. We know we can split them into protons, neutrons, and electrons, and then from there, you can go to quarks, leptons, gluons, all of the other pieces that make up the protons, neutrons, and electrons. They do combine in simple whole number ratios. This is what a chemical reaction is. But if we jump back up here, atoms of a given element are all alike. Atoms of different elements are all different. That last part is correct. If you take 2 elements and compare them to each other, they will have to be different because they're different elements. But atoms of a given element are not required to be all alike. They do not have to stay the same. You can have one atom of carbon and a second atom of carbon, and they will be different. And that might seem weird because you'd think that atoms are the base of everything that's making up the world, but it's something we're going to get into called isotopes. If you've ever heard of carbon dating uses the fact that carbon usually has a mass of 12, but it can, in a very small percentage, have a mass of 14. And that mass of 14 will slowly decay over time. So if you actually know how much carbon was in something to begin with, and you find a bone of some animal, and you measure the carbon-14 that it has now, you can track based on how much carbon-14 disappears to figure out how old something is. So if any of you who are interested in Jurassic Park stuff, doing any paleontology or anything like that, or anthropology, that's how carbon dating works. It involves the fact that elements are not all alike. So there is 3 of the flaws with this. We could probably get really nitpicky and come up with some more, but atoms are not indestructible. Atoms can be divided. Atoms of given elements are not always all alike. So those are our 3 problems with Dalton's theory. So then we jump to the 1800s, and evidence began to arise that there was not actually just kind of these little tiny indestructible things. And if I go back really quick, you'll notice I've got this blue circle over here. That's basically what he thought atoms were. He thought atoms were just these little pieces that you eventually got down to that were little spheres, and that's what they were. They were just the base component of everything. So as we go through, we'll update our model accordingly. This is kind of when we changed because of the fact that we've thought, well, okay, I don't think this is just a sphere. I think it actually has parts. We change it from the smallest part of matter to the smallest part of matter that retains the properties of that matter. And you may be wondering what exactly that means. What it means is if you have a carbon atom, for example, and you pull off the electron, that electron does not know that it was a part of a carbon atom. That electron does not have any of the properties of carbon. It's the thing as a whole is carbon, but if you to pull it apart into its pieces, it's no longer going to be carbon. You could think of it as kind of a Lego set, where if you build it and you're like, okay, this is my $250, $300 Millennium Falcon Lego set, and I've got my Millennium Falcon here, but if I pull it apart and break it down, it's no longer a Millennium Falcon. It's now just Lego pieces. So that's when they were like, okay, well, these actually can be broken down. So it retains the properties at the level of elements. But if you go anywhere below element, it no longer is going to have the properties. Your aluminum's no longer going to act like aluminum. Your uranium's no longer going to act like uranium. The first thing that was discovered was actually electrons. And this will make sense because, as we'll talk about in a little bit, electrons have a lot of weird characteristics, and they're the most reactive parts of all the atoms. Most of these discoveries came from physicists. Electrons specifically came from studying electricity, actually. And you will find that physicists and chemists have a really tight relationship. There's part of a reason that usually you have to like take chemistry before physics, or in the case of here and a lot of other schools, the teacher who teaches chemistry also teaches physics. They are actually very interconnected with each other. As opposed, they kind of hold their scientific root from alchemy, whereas like biologists hold their root from naturalists who would go out and collect things and gather specimens and observe things. So you could think of science as those two things, and then they both eventually split off and kind of connected to each other somehow. So the guy we give credit for is J.J. Thomson. This is not the guy that wanted pictures of Spider-Man. That's J. Jonah Jameson. J.J. Thomson noticed that when electricity was sent through a vacuum tube, a beam would appear, and it would go from the negative end, which is the cathode, to the positive end, which is the anode. I know it's weird that usually we think of as like a negative thing. This is because electricity and physics people label things backwards from how we think of it in chemistry. Just don't worry about it. You don't have to know the cathode anode part. But basically, because it was going from the negative to the positive, that it must be negative. So he decided to test it. And the way he tested it was by using a magnet. So not only was the beam coming from the negative end, but it would actually react to a magnet. It would attract to the positive side and repel to the negative side. I wish I had, the power source looks like it's dead for our vacuum tube, but I can actually show you what this looks like. But you can literally hold a magnet towards the beam and it will pull the beam up or down. If you put a positive on the top of it, it will pull it up. If you put a negative, it will go down. He also noticed that the source of this beam did not matter. It didn't matter what you plugged in as your source of electricity. It could have been a copper coil. It could have been anything, any other chemical battery. In modern times, you can plug it straight into your outlet. No matter whatever source you used, the beam always behaved the same. So he thought that this must be something fundamental about elements, or about the nature of matter. There must be these little negative things, so he called them electrons. I believe they were originally called like corpuscles or something like that, but we now call them electrons, which sounds at least a little bit more reasonable. Now I'm going to make sure I don't need to go on first. So they kind of updated the model, and they said, okay, well, I guess that the idea of it just being kind of a solid ball is not the case anymore. So they said, well, there's got to be something holding these electrons here. So Thomson theorized that there were negative electrons, or there was corpuscles, that were just floating around inside of this kind of area that was vaguely positive. And you might be thinking, that just sounds weird. That doesn't really make a lot of sense to us now. But again, you have hundreds of extra years of like additional scientific research, and you've heard about atoms probably for a long time in your life. So it made sense to them. They didn't have a baseline. They just thought, well, there could be this vague area of positiveness that has specked inside of it little tiny negative dots. This became known as the plum pudding model of the atom. And you might be going, why is it called the plum pudding model? It doesn't make a lot of sense. Well, first of all, he's British, so pudding does not mean like this isn't like purple goop that you're like eating with a spoon. Pudding is a term used for like baked goods. So think of like a fruit cake or like a banana bread kind of thing. That's kind of where we're going when we're talking about a pudding. And then for plums, you can basically just think of it as like raisins in there. So you could think of this as basically a circular pastry, and you've got specked inside of it little plums or little raisins. If we were doing this today, we would probably call it like the chocolate chip cookie model of the atom, where the cookie dough would represent the positive space and the chocolate chips would represent the negatives. But I guess they were just old, boring British people. They didn't have chocolate chip cookies back then. They hadn't colonized enough of the world to have stolen chocolate enough to be able to make those. So instead, they put plums in them. So electrons were easy. And you might be thinking, okay, well, what's next then? Are we going to do protons or are we going to do neutrons? But actually, you'll realize that there is something missing from that picture up there. And the thing that's missing is there's no nucleus. We don't even have a location for protons and for neutrons. So the discovery of the nucleus is actually the next piece of the puzzle. The existence of the nucleus wasn't discovered until 1911 by Ernest Rutherford, and it was through his gold foil experiments. And this is where I'm going to cut off this video, because the gold foil experiment I will probably talk for quite a long time. It's one of my favorite parts about chemistry. It's one of my favorite stories in all of chemistry. So we're going to cut off the video right here. I hope you guys could understand what was going on here. If you have any questions, you can leave a comment on this assignment, or you can send me an email. Send me an email is better. You can hop into the Zoom after school if I have free time during the day, or you can pop in on Friday and I'll answer any of your questions if I'm not recording videos like I am right now. There might be people waiting in the Zoom for me. I don't really know. But I hope you guys have a great day. I hope to see you, hear from you soon. Good luck.